Now we'll see the Bode plot of quadratic factors. So the quadratic factor will be, or the quadratic transfer function will be a form of omega n square s divided by square s square plus twice zeta omega ns plus omega n square, where omega n is the natural frequency and zeta is equal to damping ratio. So we have to change it into the form compatible of the Bode plot, and we just put s is equal to j omega in this equation, and we take omega n square common from numerator and denominator. So in this way we get the equation changed into the form of this, that is gj omega is equal to 1 divided by 1 plus twice zeta j omega divided by omega n plus j omega divided by omega n square. So so this is basically our quadratic factor, and we will try to draw the Bode plot for these kind of factors. So first thing is that we just see that the denominator is in the form of a quadratic equation. So we first calculate the discriminant of this quadratic equation, and the discriminant is equal to b square minus 4ac. So this is basically of the form ax square plus twice, or in fact x square plus bx plus c. So the denominator in this form, so clearly b is equal to twice zeta, and a is equal to, value of a is equal to 1, and c is also equal to 1. So if I put the value of a is equal to 1, c is equal to 1, and b is equal to twice zeta in this equation of discriminant, we get the value is equal to 4 zeta square minus 4, and it is equal to 4 zeta square minus 1. So this is our value of discriminant. So clearly if the discriminant will be greater than 0, greater than and equal to 0, we will get a real poles. As for discriminant greater than 0, the solution of this quadratic equation will have real values. So similarly this equation will give you the location of pole. So clearly for discriminant greater than 0, you get the quadratic factor as the product of two first order factors with real poles. And in this case this is the case of overdamped system, and in case of overdamped system we have already learned that the response is sluggish. So real part of the pole may be positive for the unstable system, or it may be negative for the stable system. But the thing is that the real part, the pole is real pole. There is no any imaginary component in this pole. If zeta is greater than 1, then the pole lies on this this line. So if this is equal to sigma, this is our j omega, as we already learned that s may be written in the form of sigma plus j omega, then the pole will be lie on the real axis. So clearly if the pole lies on the left half of j omega, or in the negative side of j omega axis, then it is a stable system. And if the real part of pole is positive, then it is an unstable system. So similarly for zeta greater than 0 but less than 1, so it leads to an underdamped case. In this case poles are complex. So in this case we have pole having two components. One is the real component and other is imaginary component. And we have already learned that in case of underdamped case, the response is having some peak value, and about such kind of response we will learn in this section. So how we will draw the Bode plot of this quadratic factor. So consider this quadratic factor. First we will try to draw the log magnitude curve, then we will try to draw the phase curve. So for the log magnitude curve, we take the mod of this transfer function and put it in the form of 20 log mod z omega. So if you take this mod of this, and then you just square the real part and imaginary parts. So here the real part is equal to 1 minus omega square divided by omega n square. This is our real part, and the imaginary part is equal to twice zeta omega divided by omega n. So if you take the square root and add this, you will get the value of magnitude. So twice zeta omega divided by omega n square, and you get the magnitude of this value. And so minus 20 log square root 1 minus omega square divided by omega n square, the whole square, plus twice zeta omega divided by omega n square. So now we will consider different conditions. First is for the low frequency components, that is omega very small in comparison to natural frequency omega n. Then in this case, if the value of omega is very small in comparison to omega n, we can straight away reduce this component equal to 0 and this component equal to 0, or in fact we may ignore these two components and the whole expression will be changed to square root 1. So the log magnitude curves becomes minus 20 log 1 or a 0 dB line. So the low frequency component is thus a horizontal line at 0 dB. Now we consider the high frequency component. So high frequency component, in case of high frequency component, what we will do, that is for omega much greater than omega n, and we have omega divided by omega n is much greater than 1. So clearly we have two components in the form of omega divided by omega n, and first is of the square factor square form, and other one is in the linear form. We can definitely ignore the linear form also. So it will be changed to, this equation will be changed under the condition omega greater than omega n is equal to square root omega square divided by omega n square whole square under the square root. So I have done this very same thing, and if you see, then this equation will be changed into this form: minus 20 log omega divided by omega n square. So clearly the value is equal to minus 40 log omega divided by omega n dB, and the value is equal to minus 40 log omega plus 40 log omega n. So clearly the high frequency asymptote is having a line having slope minus 40 decibel per decade or minus 12 decibel per octave. So how we get this minus 40 decibel per decade? That is, if you make omega, if you replace omega by 10 omega, then you can see that this will be changed by the value equal to minus 40 dB, while remaining term will be the constant. So the slope will change by a factor equal to minus 40 dB per decade or minus 12 dB per octave. So now we will calculate the intersection of high frequency asymptote to the low frequency asymptote, that is when these two asymptotic approximations actually meet. So for this we just put these two value equal to each other. So first value is equal to 0 dB line, and second value is equal to minus 40 log omega plus 40 log omega n line. And if you keep these two value equal, you get the value is equal to log omega is equal to log omega n, and it will equal to omega is equal to omega n. So this is the point where these two frequency asymptotes actually meet. So, and this frequency is called as corner frequency. So we get the corner frequency is equal to omega is equal to omega 1, and for the below the corner frequency, the low frequency response is termed equal to 0 dB, and the high frequency response is equal to minus 40 log omega divided by omega n for a pole. That is if the quadratic factor is in terms of pole and in the form of twice zeta omega by twice zeta j omega divided by omega n plus j omega divided by omega n square. So while the slope for 0 will be 40 log omega by omega n, and the second order 0 will be a form of 1 plus twice zeta j omega by omega n plus j omega by omega n square. So if this terms comes in the numerator, then we get a slope equal to plus 40 dB plus 40 log omega by omega n for the high frequency component, and if this quadratic factors comes in the denominator, then we get the slope equal to minus 40 decibel per decade, and the high frequency response is equal to minus 40 log omega divided by omega n. The role of damping ratio zeta in the quadratic factor. So as we have already learned that for a quadratic pole, the equation or the Bode plot can be approximated by two asymptotes, one having the value equal to 0 dB and other having the value equal to minus 40 log omega divided by omega n, and these two asymptotes meet at the point omega is equal to omega 1, that is at the corner frequency. So basically these are two asymptotes which meets at the point omega is equal to omega 1, and this line is having a slope equal to minus 40 dB per decade. We have also learned that the first asymptote is the 0 dB line, and the second asymptote is equal to minus 40 log omega by omega n. So ideally these two asymptotes are independent of the value of zeta, that is damping ratio. But near the corner frequency omega is equal to omega 1, I have already drawn the figure of a quadratic factor, and you may see from this figure that near the corner frequency omega is equal to omega n, we have seen a resonant peak. So the magnitude of this peak is determined by the value of zeta. Clearly from the figure, for zeta is equal to 0.1, we have the value of peak will be more in comparison to other values of zeta. Again, if you see that for the value of zeta approximately equal to 0.7, we have not seen any peak. So clearly the error in the magnitude approximation depends on the value of zeta. So the error in the magnitude approximation we have done depends on the value of zeta, and smaller the value of zeta, we get a more peak at the point omega is equal to omega n, that is at the corner frequency.